Here with us today, we have Dr. Steve MacLaren. Steve is a design physicist in weapons and complex integration at Livermore. He came to Livermore in 2000 following his PhD at the University of California, Berkeley. At Livermore, Steve has led the program element for high energy density experimental design and has designed targets for high energy density experiments at Z, Omega, and NIF. Steve is currently working on multiple projects within the ICF program and leads the Pushered Single Shell effort. So this talk will be recorded. So if you're uncomfortable with that, please sign out, and anything that's said will be part of that record. Also, please be aware this is an unclassified meeting, and we also have external people logged on. So be wary of any export control issues. Otherwise, I very much look forward to Dr. MacLaren's talk, and please take it away.
Thanks, Paul. I'm assuming you can still hear me?
Yes.
So yeah, my name is Steve MacLaren, and this talk's title is The Alternate Approach to the Ignition Regime for Inertial Confinement Fusion, and I'm presenting on behalf of a Pushered Single Shell team, which is a fairly decent-sized collaboration between Livermore and General Atomics. So what I'll be describing is a slower, more massive implosion, which we call the Pushered Single Shell. It offers a fundamentally different trajectory towards the ignition threshold. I'm going to start by describing this threshold, sort of developing an analytic theory, and then using it to motivate the design of the Pushered Single Shell, which the idea being that it reaches the ignition condition at a lower velocity and temperature, so it a little bit easier constraints than pushing the implosions up to very high velocity with low Z ablators. Then I'll talk about some of the challenges that we've faced. We've been able to use the ARC, the Advanced Radiography capability, and together with the indirect drive platform on the NIF, and then we've demonstrated tunable long pulse implosions of the kind that you would need for a low adiabat compression of cryogenic fuel layer for ignition. The shell is a graded density profile. And it's been successfully fabricated into beryllium capsules at General Atomics. And this profile predicts to mitigate the ablation front instability so as to allow good compression at the increased confinement that you get from the more massive pusher. And so this plot on the right is sort of the key plot that we'll come back to a couple times in the talk, but the takeaway is that I'm plotting in this space of p tau, versus ion temperature, the pressure times the confinement time versus ion temperature, sometimes referred to as a generalized Lawson criterion, as it's sort of a measure of the relative energy of the hot spot from alpha heating versus the stagnated energy of the hot spot. But in this plane, we're going to define this threshold, a burn-on threshold, as it takes into account the process of alpha heating. We're going to define this threshold, and we're going to show where some of these implosions cross it, the implosions down here being the low Z ablators, and the implosion up here as we increase each one of these is a simulation with increased drive energy, being the Pushered Single Shell. Pushered Single Shell is happening at a lower velocity and takes advantage of the increased confinement to cross over the threshold at a lower temperature. So like I said, it's a collaboration between Livermore and GA because of the technology required to develop these ablators. At Livermore, I wanted to point out Eddie DeWald, the lead experimentalist. David Martinez has been key to bringing the ARC capability up to do the radiography in flight of our implosions. And at GA, Hongwei Zhu has really pioneered this technology for us of grading in the mid-Z material into the beryllium ablator to give us our graded density profile in the shell. So I'm going to start with this theoretical description that helps motivate why we go in this direction for a design, for an implosion design for ignition. So the ignition condition, we start with sort of an ansatz that the ignition condition can be described as a race between the rate of alpha heating on the one hand and the disassembly rate on the other. And so in this figure, the solid curves, the red and the black curve, represent the heating rate, the energy production rate, I should say, for a burn-on or an implosion simulation with alpha deposition and one without. So you can see that there's, without alpha deposition, the peak of the energy deposition sort of defines the phases of compression and expansion in the implosion. Once you turn on alpha deposition, your energy production rate continues past the peak compression and into the expansion phase. And this time is sometimes referred to as the bootstrap time, because it's the time during which, if your temperature is high enough in the hot spot of your implosion, you can continue to produce energy well past the peak of compression, and that energy that you are producing, that you started with during compression and bootstraps, into the total energy produced in the hot spot in the implosion. And so all of this is happening provided the ion temperature is high and is continuing to increase during this period of heating. And so if the heating rate then is greater than the disassembly rate during this critical period, you will get significant energy production and yield amplification. So we'll start off in defining the heating rate. We'll start off with the hotspot power balance. So this middle equation at the top. If you were at the seminar 2 weeks ago, Brian Appleby actually did a nice job of sort of graphically describing the pieces and parts of the hotspot power balance. But this equation just says that in the hotspot, the temperature as a function of time will depend on the contribution of alpha heating, which is the main source for energy, but also the losses due to Bremsstrahlung, conduction, expansion due to PDV work, and possibly other losses. Over here, we're just defining the hotspot thermodynamics, the power, as being both a function of the temperature change as well as the mass change in the hotspot. And then referring to the mass, the accretion assumptions, basically this is a statement about what's happening at the edge of the hotspot. This first term represents the fact that alpha is produced from fusion that don't deposit in the hot spot will deposit in the cold fuel immediately adjacent to the hot spot, and that will add mass to the hot spot. Similarly, the conduction layer, as electrons conduct heat away from the hot spot, is a very thin region at the edge of the cold fuel, and as that happens, that will heat up the cold fuel and add mass to the hot spot. So these are these mass accretion assumptions. And of course, these assumptions are only valid for a cryogenic fuel layer case. So when we combine these, we can combine these in order to form an expression for the net heating rate, which essentially has a static term that is representative of the inherent alpha source, Bremsstrahlung losses, and then this dynamic term, which is the PDV work. So we recognize that the static heating rate is really just a function of pressure and temperature. So we write it as F of T, and then the dynamic losses are over here. Fortunately, this average heating rate has already been calculated in a paper by Hurricane a year or so ago in Physics of Plasmas. And what we do is we regard this heating rate as being a very peaked function, and I'm plotting it here again with the power, the energy production rate as well. But this heating rate in the calculation is very peaked function, and it's peaking always during the bootstrap time. So this is the time over which we want to integrate this heating rate in order to come up with a meaningful integrate this expression in order to come up with a meaningful expression for the heating rate. So it's essentially the integral of this static heating rate over the bootstrap time, which then also turns into a nice analytic expression in terms of the temperature. So we'll go through that briefly. I apologize. This slide has a lot of detail on it, but it's sort of for the record, so that we can understand that we can get an algebraic form for the temperature in the heating rate. And Hurricane does this in a paper that's just been accepted to Physics of Plasmas by fitting the fusion reactivity. This F of T function that comes out of our net heating rate is really dependent on temperature through the fusion reaction rate from the alpha depositions. And so Hurricane fits the Bosch and Hale formula for the reaction rate with a couple parameters, and then that produces a very nice fit to this F of T function over the range from about 2 to 10 kilovolts, which is, the important range as you're approaching ignition in a hot spot. So with this fit, we can write down a functional form for F of T in terms of the temperature, recognizing that it's a very peaked function during the time of interest, during this bootstrap time. Hurricane uses the method of steepest descent to come up with an analytic expression for the result, which then can be turned into an algebraic expression using this fit. And we arrive at a nice algebraic expression that we can use both for theoretical analysis, comparison with simulations, and comparison with data. So it's a nice result. Now we're going to talk about the disassembly rate, which is the other piece of the ansatz, heating rate versus disassembly rate. So here, this is during the expansion phase. We look at the PDV work. dVdt is 0, of course, at minimum volume, but we want to expand about minimum volume to try and get an understanding of what's going on with that part of the implosion. So with this expansion, we come up with two terms: the sort of acceleration term, and then this term that represents a residual 3D shell velocity, which we'll set aside for this 1D analysis. Additionally, we consider the relationship between the acceleration and the stagnated mass. That's just Newton's law, the force exerted by the delta P across the stagnation shock at minimum volume. And then the final important thing to recognize is that we can write the combination of the stagnated mass, hotspot, pressure, and radius in terms of the confinement time. So we'll identify our expansion time as the confinement time, and then we can write it in terms of these other parameters. And so when we do that, now we can go back to our expression for the heating rate and write out the dynamic piece, this dynamic expansion term, in terms of hotspot pressure, radius, and stagnation time. Stagnated mass, which then can also be written more simply in terms of 1 over the confinement time. So now we have something that we recognize as a rate, as a disassembly rate, and we can compare it against the heating rate, and we can understand this as a requirement that the net heating rate near minimum volume should be positive if we want yield amplification. So when we write down that requirement of the heating rate is greater than the disassembly rate, one thing that we notice is that there's a relationship. If we combine the pressure and tau, there's a relationship that shows that the p tau does go like the square root of the stagnated mass. So if we want to, one way to increase our p tau is to increase our stagnated mass. But in addition, as we turn this condition into something that looks more like the generalized Lawson criterion, so an expression for p tau as a function of temperature, then we can compare that against another GLC. And here on this plot, I'm comparing the relationship that I've just gone through with this 1 over h of t function. This is the analytic function from a few slides ago, with another burn-off GLC, so a criterion that's using just quantities in the implosion without alpha heating. And so this is a simpler, more straightforward expression in that it doesn't include, it avoids the consideration of the nature of the alpha heating. But when we plot burn-off and burn-on simulations against these two criteria, we find that the yield amplification as you cross the burn-off criteria for these BigFoot implosions is actually quite low, whereas for the BigFoot series here, where I'm turning up the drive, we see that we cross the criteria somewhere around yield amplification of 20, which is more consistent with an ignition threshold. So the assertion is that by using a burn-on metric, we're actually better capturing this idea of a race between the competing effects of heating and disassembly rate. Okay, so now we're going to look at the design, or the description of the design of our Pushered Single Shell, and use this idea of the enhancement in stagnated mass and its effect on p-tau to motivate our design. So to increase the mass of stagnation, the Pushered Single Shell design uses a graded density inner ablator layer. And so I've mocked that up in this cartoon. This is what we call a pie diagram representation of the Pushered Single Shell capsule for the NIF design. It's 1.2 millimeter outer radius. There's a lot of pure beryllium here that serves as the ablator to get the shell moving from the X-ray drive. But then we ramp up the density as we add chromium into the beryllium. There's a thin inner layer of pure beryllium that we describe as an anti-mix layer. More on that later. This is our suspended cryogenic fuel layer, and of course there'll be DT vapor inside of that. So in terms of the radial profile of what's going on in this graded layer, that's shown here on the right. And I'm showing two different designs. The blue represents our layered design, and the red is what I'm calling the HED design, which is the design that we're actually currently shooting on the NIF for the high energy density program, where the Pushered Single Shell platform is vectored towards optimizing a platform to look at mixing of mid-Z and high-Z metal in the presence of a fusion hotspot. So these are these two designs. The layered design is thinner. It's really optimized to accommodate the additional mass of the DT fuel as well as to increase the velocity a little bit in the implosion to get over a temperature threshold. So with that in mind, I wanted to point out that the Pushered Single Shell, the concept of Pushered Single Shells for the laboratory is not really a new idea. In fact, there's papers going back to late 80s, early 90s describing the Pushered Single Shell implosions for IFE. Then importantly, in 2000, there's a paper by Wilson that describes a design of a cryogenic DT-layered beryllium Pushered Single Shell with a solid tungsten layer, 6 micron of solid tungsten on the inside to give it the enhanced tamping mass. Then next, there's a physics plasmas paper by Jose Milovich that describes use of a graded density shell as a means for mitigating the instability in the heavy shell implosion, and that was revisited again recently by Hu et al. And then finally, bringing in the graded beryllium NIF design was first described by Perkins at DPP, and then later by Ho et al. At an anomalous absorption meeting. So the technology that now exists that is allowing us to take advantage of this design concept in the laboratory is developed by General Atomics. And they've demonstrated the ability to put it into quality capsules, production capsules, smooth, high quality graded shells. So this is really what's given us the opportunity for viable implosion experiments on the NIF. And in the center plot, I'm showing a comparison of the chromium atomic fraction as delivered in a recent set of capsules by GA. The requested profile is in red. This deviation from the requested profile here is actually just a function of this particular measurement technique used to pull out the absolute atomic fraction. Other measurements show that we are actually achieving a very steep transition between the beryllium and the chromium here on the inner layer. This is showing the roughness of the surface of one of these completed capsules, where we're doing as well or better than the copper doped beryllium capsules that have been used in ICF program experiments on the NIF to date. One other interesting nugget that's come out of the work is this coating work is that as the coating transitions from pure beryllium to this higher concentration of chromium, somewhere around halfway, the morphology of the metal actually goes from crystalline to amorphous. This could potentially be a benefit because these crystals and crystal boundaries can be seeds for instability growth. And as we go towards the inner surface, towards the fuel ablator interface, all of a sudden these crystals disappear in the imaging. So we have a very strong collaboration with GA, and these results really represent more than 2 years of dedicated R&D on this fabrication and production technology. We're currently applying it to molybdenum, blending beryllium with molybdenum for sort of the next phase of these designs, and we continue to meet with every week or two with our collaborators at GA. So in terms of turning this into an improvement in the stagnation, I've got a comparison here between a low Z ablator, a BigFoot implosion, and the PSS, and this hopefully will help identify the advantage of the additional stagnated mass for the burn width of the implosion. These are 1D no alpha simulations, so there is no alpha deposition on. So the idea is to highlight the behavior of the hydrodynamics on the fusion burn. And so in the BigFoot simulation, both implosions reach about the same pressure without alpha deposition. And I'm plotting the rate of fusion energy production. So you have sort of a burn width of 90 to 100 picoseconds. You can see the hotspot radius. Here's sort of minimum volume. And then the RT profile is of the density reaching peak density at near minimum volume. On the other hand, for the Pushered Single Shell implosion, the density profile now clearly highlights the location of the stagnation shock. And so the stagnated mass is really this mass that's contained between the hotspot and the stagnation shock. And that stagnated mass is, as you can see graphically, is considerably more in the Pushered Single Shell than it is in the low Z implosion. And so just from the simple theory, you would estimate that the stagnated mass the enhancement of the stagnated mass should increase the confinement time by about a factor of 2.2, and in fact it's increasing it in the simulations, very close to that by about 2.4 when the radius is taken into account. So we can demonstrate through simulation that the simple theory of increasing the confinement time through the stagnated mass seems to hold up. So if we look further using these 1D simulations at our definition for the threshold through yield amplification, we can essentially validate this analytic theory with these 1D simulations, and then in addition to that, use this to highlight the difference in the approach to the ignition regime the Pushered Single Shell represents. So on the left-hand side, what I'm plotting is the trajectory through yield amplification of, again, 4 different implosions, 3 low-Z implosions, and the purple one being the Pushered Single Shell. So there's a copper ablator, HDC ablator. The high foot is the CH ablator, and then here's our graded density Pushered Single Shell. And as I take the same implosion and simply increase the drive, pushing up the yield amplification in the implosion, I can watch where these implosions cross this threshold that I've defined by setting the heating rate equal to the disassembly rate. And so here's the threshold, p tau h of t equals 1. I can track that threshold as the simulation advance. And in each case, the simulations cross the threshold as the yield amplification is in the vicinity of 20 or 30, which is typically a definition used for the ignition threshold. So for a broad class of implosions, this simple theory seems to be holding up when tested against a variety of these 1D simulations. But when we plot it again in this space of p tau versus t, that's where we separate out what's going on with the Pushered Single Shell as happening at a much higher value of p tau due to the increased confinement, and then at a lower temperature, which allows for a lower implosion velocity. And then I'm scanning here. The PSS design gets scanned with drives that were calculated from laser energies NIF laser energies between 1.7 and 1.9 megajoules as it crosses over this threshold. Okay, so with sort of the theory laid out and the motivation laid out, I want to next go through some recent results on the NIF that we've achieved with the Pushered Single Shell in the experimental realm. So when we implode these on the NIF, it's an indirect drive implosion, and we design the indirect drive implosion using rad HYDRA tools. In this case, I'm using the configuration managed LASNEX simulations to calculate the integrated laser hohlraum capsule implosion. On the left, just to describe the simulations, it's a common model that's being used for a wide variety of indirect drive implosions on the NIF, including some platforms that are actually designed for focused hohlraum physics. The view factor platform, the glint platform. So with one model, we try and incorporate the best practices and capture all of the most recent data for hohlraum implosions, and then we can apply it to design for implosions on the NIF, and that's what we're doing here. We're using right now in the HED PSS campaign, we're employing 2 different pulse shapes to look at the trade-offs between stability and performance. We've got a 2-shock pulse shape and a 3-shock pulse shape. This is a pre-shot, and then the post-shot here is coming from an actual shot, the laser power history of an actual shot that we've done so far in the campaign. So with these integrated simulations, we can predict the velocity and the spectrum and then, of course, the symmetry of the capsule implosion. We would like round implosions. We can use the simulations to predict what will happen when we make adjustments to the laser, in this case, the wavelength separation of the laser, in order to improve symmetry. Here I'm showing simulations that were done at 1 angstrom and 1.3 angstroms in the wavelength separation to try and improve the symmetry. These are radiation temperature histories that we get out of the simulation for the different pulse shapes. Now, the simulations are great to predict what the symmetry is going to do, but we need to be able to make those measurements in the laboratory to understand if we're achieving what the simulation is predicting. These are examples of a nicely well-behaved implosion in the laboratory, where we're using two techniques. This is the 2D Con-A, which is a backlit imaging, area backlit imaging of a plastic capsule on its way in to stagnation through minimum, I should say through peak velocity of the implosion. And then at stagnation, these are X-ray images, X-ray self-emission images, as the X-rays of the fusion hotspot escape through the remaining plastic ablator. So backlit X-ray transmission images and X-ray self-emission images are typically what's used in the laboratory to establish the velocity and symmetry of the implosion. Unfortunately, neither is going to work for the Pushered single shell because the area backlighters won't see through the implosion, and at stagnation, the X-rays won't get out. In particular, here's our HED PSS design with the 50% chromium atomic fraction that's ramped up to the inner surface of the capsule. These are some simulations Chris Young did of in-flight implosions with various backlighting spectra attempting to see through the implosion near near peak velocity, where we like to understand the in-flight shape. And this blue curve here is showing the zirconium backlight, which is just about the hardest K-shell area backlighter that we could employ in the typical 2D Con-A platform. It's not making its way through the shell. So we then decided to use some Bremsstrahlung spectrum that were calculated from arc beams on a gold wire, and realized that's what we were going to need to see through the imploding shell for the PSS. So we went ahead and designed this platform that uses arc to see through the shell in flight, and it uses 2 gold wires to get a sequence of 2 images separated by the lines of sight through the hohlraum onto an image plate. So this is the radiography axis between the arc targets and the hohlraum in the capsule. Some details of the configuration are here. Importantly, we took advantage of a technique that uses a sort of a plasma mirror based approach. It's what we call a U-flag that helps focus some of the arc energy onto the gold wire and increases the brightness of the gold wire spectrum onto the target. When we did this on the very first attempt, thanks to a lot of dedicated work by Dave Martinez, on the very first attempt, we got an in-flight image of our imploding chromium shell. We got one early image. Unfortunately, we didn't see the late image, but some good detective work by David showed that the early beam was actually clipping or splashing onto the U flag for the late beam. And by a combination of repointing and delay, David modeled the incident energy onto the U flag and decided that with a little bit of a displacement and a little reduction in the delay, we could really help ourselves and improve our chances of getting that late image. And sure enough, it worked like a charm. The next implosion we did in May of last year, we got 2 images on both sets of detectors. You can see there's hohlraum background that gets onto the image plate because it's a time integrated emission measurement. But what happens is we can use a gated detector called Axis to gate out that hohlraum emission and remove it, and that's shown on the lower images. We then immediately applied this platform to go to some tuning shots. We made some changes in the pulse shape that changed the implosion to pancaked, and then we straightened it out with a change in the wavelength separation between the inner and outer cones, and we got a round implosion. Let me just go back to that slide. Sorry about that. Superimposed on our arc images, on our transmission images, are neutron images. So we're not seeing X-rays from the core, but we do capture neutrons. And even with a DD fill, we're able to produce enough DD neutrons to get reasonably accurate shape images at stagnation in the equatorial neutron imaging system. And that allows us to sort of track the shape behavior as we went through this scan in delta lambda to push our implosion round, we can compare the core image P2 as well as the shell image P2. We can see that both track together, showing that any symmetry swings we have would be quite small, and that we can tune the implosion round. So with that tuning campaign, demonstration of tuning success, we did a couple of DT Symcaps to sort of test the tuning playbook and actually give us a first indication of the efficacy of enhanced confinement on the fusion performance. So shown here are neutron images, equatorial neutron images from a pair of these Symcaps where we once again used the delta lambda to tune the implosion round following a pulse shape change. And on this second implosion, what I'm showing here is an example of a 2D integrated, 2D capsule-only detailed high-resolution post-shot simulation done by Jesse Pino in Aries that takes the surface roughness that I showed earlier, the actual surface roughness in the capsule, propagates it into the implosion at stagnation time, giving you an idea of what how the ablator is behaving in this metal gas implosion at stagnation, and what type of degradation we might see to a clean yield prediction. And so that's actually the simulation in this simulation did a quite good job of predicting the sort of 35% degradation to the clean yield that we ended up seeing in the data, and that's the data over here. This table, what I'm doing is I'm comparing the data from our Pushered Single Shell shot with data from a comparable low-Z DT Symcap. So this is a HDC capsule without a cryogenic layer, but filled with DT gas, very similar inner radius. The key difference here is the low-Z implosion is going much, much faster than the Pushered Single Shell. And so you would expect, because of that, you would expect a much higher stagnation temperature. But even with those factors, the performance of the two implosions is actually quite similar. Also taking into account the degradation that we're seeing from the mixture of the mid-Z chromium into the annulus of the implosion. So this is a strong indication that at low velocity and low temperature, we are still able to recoup the benefits of the enhanced confinement in order to nearly recover the performance of the high velocity low Z implosion. So that sort of summarizes the results to date on the NIF. The last thing I want to do in the sort of 10 minutes remaining is take a look at the stability of the layered PSS design, because of course with the mid-Z, high-Z dopant in the shell that we have in our designs, if that shell goes unstable and pollutes the cryogenic layer, then we don't really have much hope of achieving gain yield and yield amplification. So we need to carefully assess the stability of the implosion with that graded density layer in order to see if we have a chance of getting to realistic yield amplifications. So the gradient design is specifically in there to provide for stability at the ablation front and minimize the growth at the ablation front. But the fact that we have a very heavy inner layer gives us a big advantage over the low Z in terms of the fuel ablator interface, because we are classically stable all the way through the peak velocity. And so this is comparing the Atwood number at the fuel ablator interface from peak acceleration up to peak velocity, comparing it with what would otherwise be a very favorable implosion, which was this very stable BigFoot implosion, which was also predicted to be stable, but showing that the addition of the mass at the inner surface really helps us, stay classically stable all the way through peak velocity. I'm plotting two curves for the PSS. We have a density match design to the chromium design that I showed earlier for molybdenum. Like I said, we're in the process of developing that coating technology and fabrication for molybdenum as well as a chromium graded design. But on the right-hand plot, I'm comparing the density gradient scale length at the ablation front. And so this is what the ablation front is seeing as it's pushing on the shell. And you want to make the density gradient scale length as long as possible in order to mitigate the growth of instabilities at the ablation front. And so typically that scale length tends to get small at peak acceleration. But here I'm showing that both of these designs have a scale length that's up here around 15 microns that is also comparable to this very stable BigFoot implosion, what's calculated for that scale length. So even though the BigFoot implosion is just a low Z sort of pure carbon ablator, and we have these high Z graded layers, the design of the gradient is keeping this scale length at the ablation front propped up and comparable to what we see in the low Z ablator. So those two factors help us, and we can see that in terms of looking at growth factors for Rayleigh-Taylor growth in the capsule, both at the ablation front and then in at the hot spot. And so these are calculations done by Darwin Ho, a series of calculations to look at the growth factor at different specific modes using HYDRA. And they're compared again against a adiabat or an HDC, a diamond ablator implosion of similar adiabat to our PSS design. And basically, the ablation front, what you see is that you're going to get helped by two things. You're going to get helped by this ablation scale length on the previous slide, as well as the enhanced ablation velocity that you get from the beryllium over the diamond, and so that helps keep the growth factors at high mode for the PSS lower than for the HDC implosion. And then at the fuel ablator interface or at the hot spot near stagnation, the PSS is just taking advantage of a reduced deceleration because it didn't reach as high a velocity as well as a good Atwood number to reduce the growth factors there. And so with those reduced growth factors, when Darwin puts all of these together into a high resolution capsule-only simulation to look at the full implosion at stagnation, once again using the measured surface roughness that we're getting from these capsules through the fabrication at GA, we do see that we're getting good confinement of the fuel at ignition. And so the left-hand plot is at ignition. The right-hand plot is further on in the simulation, past ignition to peak energy production. At ignition, we see that our good fall line behavior, the good deceleration stability that's resulting from a lower peak velocity and a shorter time to decelerate because of the enhanced momentum in the shell. That's what's keeping sort of the fuel ablator interface intact. These are the different regions. The dark blue here is this beryllium anti-mix layer that I described earlier, and that's helping us keep the fuel clean at ignition. Later on, as this interface is now classically unstable, we're going to see some growth at the fuel anti-mix layer boundary that's going to begin mixing in the ablator, and this is ultimately what's going to limit our performance during an igniting capsule. But overall, these studies, simulation studies, 1 and 2D and low and high mode, indicate that we do have good stability with this graded design. So with that, whoops, I went one too far. With that, I'd like to just sort of summarize and come back to this original plot. That is the key motivation separating the Pushered Single Shell design out from other approaches to ignition. So we've come up with an analytic description of the threshold in this space of p tau versus t that allows us to clearly separate out where the trajectory of the Pushered Single Shell implosion is as it crosses the ignition threshold at lower temperature and lower velocity. I've described how we stood up this platform on the NIF. A lot of great effort from the experimental team. We've used the advanced radiographic capability, the ARC, to give us our in-flight imaging to examine if we've got the right implosion velocity and if we have any symmetry swings. We have a long pulse, as I showed. It's about a 13 nanosecond pulse. So we need to be able to demonstrate that we can control implosions for that long pulse, control the symmetry of those implosions. And then finally, the work at GA, the sort of pioneering effort, technological advances there to successfully produce high-quality capsules is really what's been the key to bring this design, into reality, and give us the prediction through the ability to precisely match our specified density gradient that we can maintain stability in a layered implosion and actually get to this place where we're headed towards the ignition threshold. So with that, I'd like to wrap it up and take questions.
Thank you very much, Steve. So please enter your questions in the chat field. And also in the meantime, invite everybody to unmute yourself so we can give Steve a nice applause. And I also saw that Eugene Henry had a hand raised earlier.
So I see Dave Montgomery's asking about the DD yield, and to get neutron images with the DD implosions is tricky, but with DD yields that were right around 10 to the 13, 9, 10 to the 12, 10 to the 13, we were able to get decent neutron images on the 9315 neutron imager.
So Ben Bachman is asking, is there a plan / schedule for a DT shot?
Yeah, good question, Ben. So this is a proposal that has been submitted to at Livermore. It's the Disruptive Proposal Initiative, and so we are proposing a campaign to take the layered design that I showed, which is a slightly different capsule than the current HED design, and do the tuning shots necessary to then attempt a layered implosion. So it's a series of shots that we've requested from the DPI.
And Bruce Remington asks, what limits how large a capsule you can use?
Well, that's the hohlraum, and everything we've learned to date on the NIF about hohlraum behavior and the integrated behavior of the laser and the hohlraum, including all of the LPI that's going on. Right now, the 1200 looks to be about the biggest thing we can fit into the 672 cylindrical hohlraum, which is the big hohlraum on the NIF, and get a drive temperature up around 290 EV with sort of 1.9 megajoule drive. That said, there's potential to go to a larger capsule using some of the newer techniques like the frustum, where for various reasons the symmetry is behaving better, the coupling is a bit better because of the smaller LEH, and so we may be able to get an even larger capsule in there.
There's another question from David Montgomery for the gas-only HED design. What is the fuel rho R at stagnation and the convergence ratio?
So for the gas-only design, it's a higher pressure fill. 6 milligram per cc is the gas density. I'd have to get back to the rho R is still low in the current implosions, although once we tune up the implosion, we hope to be able to use some things to increase the drive, higher laser power, DU hohlraums. But right now, I think the gas rho R is right around 0.1, maybe a little bit less, and the convergence ratio is low. It's around 16, I think.
Hui Chen asks, how far can you push for the shell mass in this design?
Oh, great question. Right. So that's really the critical design trade-off right now between performance and stability. Obviously, increasing the shell mass, and here I'm really referring to the density at the inner layer, because we could potentially increase that density with particularly with molybdenum quite high in that inner layer. Without increasing the capsule mass significantly, because most of the capsule volume, of course, is beryllium at density 1.8. But to ramp up to that density, of course, we need to design a gradient, and we need to design that gradient so it's going to be stable at the ablation front. So right now, Darwin and I and the team have taken a fairly conservative approach to limit that peak density to about 4.25. At the inner shell, in order to sort of put a cap on the gradient of the density going up from pure beryllium to the peak density.
So KB asks, by hydroscaling BigFoot up, the confinement time increases with scale, and the scale factor of 1.4 emission is reached with p-tau closer to 40 in between the values you have on your plot.
Right. I mean, these are the red dots on the plot are the I guess you'd call it scale 1.0, the 180128 scale. And in that case, all I'm doing is I'm pushing on the drive in order to push it across the ignition threshold. So yes, if you can get a very big capsule hydroscaled, then that will have the same effect, because for a constant remaining mass, I should say a constant fraction of remaining mass, the absolute mass inside the stagnation shock will increase, and that will increase your confinement time.
Okay, are there any other questions? Well, I wish everybody a happy rest of your Thursday, and please let's thank our speaker again.